How you doing? I'm Mr. Rose, and today we're going to continue our discussion about Gauss's law. Now I say continue because last time we didn't really get to Gauss's law. We just set up a whole bunch of information so we can start to utilize it. So let's start here. What do I have drawn here? Here I have a positive charge Q, and I've already drawn out the electric field. Now our electric field gives us two pieces of information. One, we know we draw the electric field in the direction of a positive test charge, meaning all these lines are radiating outward, and we know that because, by definition, electric fields are just moving in that direction. Second, we know by this drawing that we can estimate the strength of the electric field. And we know the strength of the electric field is proportional to the number of lines per unit area. Now that sounds kind of arbitrary, because if I draw one and you draw one, they might look different. Maybe you have more lines than I do. How do we know how many lines to actually draw? Well, it's really an area density. We know that the strength is proportional to something in this area density. Well, what area am I talking about? This area density is something we're going to refer to as a flux. Well, what do we know about an electric field? We know, and we can see in this example, that my electric field falls off as a factor of 1 over r squared, and we know that from our formula. Now, if we agree, and we have to agree because you're there and I'm here, if we agree that we are going to draw the same number of lines, 1 over epsilon naught lines per coulomb. Now I know that seems weird, but if you just bear with me for a few minutes, we're going to agree to draw 1 over epsilon naught lines per coulomb for our electric field. That means if I'm given any radius, let's say radius r, where I have this purple circle, if I don't know, draw some kind of a square that maybe is, say, 1 meter by 1 meter. I have 1 square meter. Well, if we all agree to the same convention, and this is a convention at a convenience, we'll all be able to agree on the strength of an electric field. So, given some radius r, I'm going to look for the line density at some specific distance, that radius r, through this, say, 1 by 1 square from that charge. Well, if we have my breakdown here, I know Q over epsilon naught, those are my number of lines. I've got my sphere, 4 pi r squared. Put that together, I've got my definition of an electric field. The electric field is equal to Q over epsilon naught times 1 over 4 pi r squared, or what we've seen before, 1 over 4 pi epsilon naught Q over r squared. So this is just a strict convenience and definition. But I want to expand on that now. And I want to expand on that because I want to know how many lines are not going through that 1 by 1 rectangle that I drew. I want to know how many lines are going through this entire shell, that sphere that I've labeled S. Well, to do that, we've already agreed upon something. We've agreed that we're going to draw epsilon over Q lines per coulomb. And now we're going to start connecting what we were talking about last time. We're going to notice that my electric field for this small little patch is perpendicular to my surface. So my electric field is coming up perpendicular to my surface, and it's in that radial direction. I can see it's in my radial direction, so I want to define a direction. I want to define my surface. I'm going to define my surface just like I defined my UFO earlier. I'm going to define my surface as dA in the radial direction, where dA is equal to my vector space dA into the r hat, or my radial direction. So I know my electric field, Q over 4 pi epsilon naught, 1 over r squared, in my r hat direction. Well, now I want to know the flow of my electric field going through that square. That's why we talked about flow rate. So I'm going to talk about my flow of the electric field. I know for any vector, I can do that with a dot product. E dot dA, that's the flow of my electric field. So now I'm going to plug that into my equation, E dot dA. E is Q over 4 pi epsilon naught, 1 over r squared, dot dA. And now I have my r hat, dot r hat. I know a unit vector, dot a unit vector. That's just 1, so that's going to go away. And now I have E dot dA is equal to Q over 4 pi epsilon naught, 1 over r squared, dA. That is my electric field for that single patch. I want to know what is not my electric field for that single patch, but my electric field for all of the patches. Now, if you think back to last time, this is similar to what we started with. We could do this long type of integration, similar to what Isaac Newton had to do when he was using universal gravitation, except we're applying this cheat, and you don't even know we're applying this cheat yet. we just applied this flow rate. Now we're going to add up all of our patches, which means the sum, or the antiderivative, E dot dA, is the antiderivative of the integral of q over 4 pi epsilon naught, 1 over r squared dA. I'm going to pull out all my constants, and I'm left with q over 4 pi epsilon naught r squared dA, where dA is just my sphere. Well, I know my sphere is 4 pi r squared, which means now I have the antiderivative of E dot dA of q over epsilon naught, because my 4 pi r squared, all that canceled out, and I'm left with my convenience of my definition from earlier. What does that do for us? That is proving to us a few things. First of all, that proves that the electric field is directly proportional to the number of lines that are cutting through that surface. Secondly, if you notice, we defined this as a shell, a sphere, a circle, some type of easy shape. Our final answer has nothing to do with the radius, which means it doesn't have to be a circle, it doesn't have to be a sphere. It could be any shape or any arbitrary shape. What we've also done is define something that's called the surface integral, or just integrating all about the surface. So we have now gone through this long trip to define what is Gauss's law. To put everything together and try to put a cap on that, I've got this nice list. Things that we know and things that we need to put together. We know electric fields exist. Like Newton knew gravitational fields existed. We know how to draw electric field lines. We know how to define a surface, dA, and we can define its direction as a vector, dA. So we are now going to start to understand that our area can be a vector. This is vector dA. We can define a flow rate of any vector with a velocity v across the area, or the surface area really, A. From there, we can find the flow, so to speak, of the electric field through any surface as adding up all of my surfaces, the sum of E dot dA. And finally, I can define the flow of an electric field as something that is called the flux, which I've already spoken about. And flux is really just the number of field lines that's cutting through some arbitrary surface. This is everything that encompasses Gauss's law. Gauss's law tells us that the flux is equal to, now this symbol is something you haven't seen before. This symbol is a enclosed integral. It's an enclosed surface. Some textbooks actually have this as a double integral with a surface, and it's a double integral because I'm a factor of area here. But our flux is equal to our enclosed surface integral of E dot dA, which is equal to Q over epsilon naught. Now, the unit for flux is a Newton meter squared per coulomb, and you might recall that I've continually used 1 over 4 pi epsilon naught when factoring out forces in electric fields instead of its equivalent of K. The reason why we've continued to use this epsilon naught is because, as we've spoken about before, epsilon naught is something that's called a permittivity constant. And what that is the ability for an electric field to flow through free space or through a vacuum. So now that epsilon naught seems to make a little bit more sense. What else we're going to find out is, what can we do with Gauss's law? Well, we just did everything that Newton did with gravitation in a much simpler fashion by making some of these assumptions and symmetry arguments. We came up with the same conclusions, and we can find flux, or the number of field lines flowing through some surface. We can find an electric field, or we can find what we're defining as a Q enclosed. Now, the Q enclosed is really the key, or at least to me, I believe it's the key to Gauss's law. That Q enclosed means this charge is enclosed by this surface S that we did over here. This surface could be an imaginary surface. And as shown, it doesn't need to be a sphere. We're going to pick surfaces that are nice and symmetrical so we can utilize some things that we know. To continue, we can determine an electric field at any point over or around that Gaussian surface. And the Gaussian surface, again, is that imaginary surface that we're enclosing our charge in. My shape as you can see here, is completely arbitrary. What do I have drawn here? I have three different surfaces. None of them are related to each other. And we know from examining flow rate last time, we know that if my flow is perpendicular, that would give me a maximum flow rate, or a maximum, that would my E dot dA would be a maximum. We know that if somehow my field is coming in the same direction or parallel to that surface area dA, that my field would be minimal, or I'd have nothing flowing through that. So we know that the surface is arbitrary provided I can examine that at the surface. What if I have more than one charge? What if I have several charges like I have here? Let's examine what I have written all the way on the left. Here I would just find the electric field. The electric field, add them together, would be my enclosed charge. To prove that, here I have a negative Q, I have a bigger 4Q, and I have a 2Q outside. Now I know to find my charge enclosed, right? E dot dA is Q over epsilon naught. To find that Q, well, I know E dot dA is Q1 over epsilon naught. I can use that one. I know E2 dA is Q2 over epsilon naught. Now, it doesn't matter that I've labeled this one negative or this one positive. We're really looking at the number of field lines coming out. So if this was simple, I could just count 1, 2, 3, 4, 5 lines coming out, 3 lines coming in. I would know my fluxes. Obviously, it's not that simple, but we can utilize superposition of Q1 over epsilon naught plus Q2 over epsilon naught is my Q enclosed. Well, what happens if Q is negative, the charge enclosed is negative Q and positive Q? That would add up to be 0. I'd have no net charge, which means I can only have a flux if there's a net charge enclosed in the region. Lastly, if I erase these guys, and now if I just look at what I have here, this positive Q, get the same color, that positive 2Q outside is sending field lines straight through my surface. Well, here, again, I have no enclosed charge, which means the Q outside has no effect because I have the same number of lines going in, the same charge density going in as I do coming out. So my net enclosed charge would be 0. Everything works out really well when utilizing this very powerful Gauss's law. That's all I have for you this time. Please feel free to like, comment, or subscribe. Don't forget you should be keeping up with your textbook. And that's it. I have no fun. I was going to do something with flexing and fluxing. Didn't work out. You'll see me next time.